is what the scanner looks like. It has a source array that you see on the bottom, the detector array on top. Looking at the source array, it's built out of source modules. Each module has 8 sources in it. There are 4 electron emitters and then 4 X-ray tube targets in the central part, and the X-rays come out the top, as you see there. Here you see the 4 modules that we now have integrated into the source array, looking into the vacuum chamber with the cover off. That, as shown there, has 32 sources in it. The detector is a lot like the conventional CT detector in this case, but turned on its side. So it's a 64 by 192 channels. It's 192 channels in the Z direction and 64 in the in-plane direction. It's quite an achievement to put all this hardware on a rotating gantry and make it spin and balance and not fly apart. And I think that was quite an achievement by the engineers and scientists at the GE Research Center. A study that we did before we had the 4 modules in there, with only 1 module in, was of a postmortem rat. Here you see paging through a volume that was acquired in a single rotation around the animal at a very low effective MAS. As is often done, you can take that and look at the bones as you in a 3D rendering approach. The 32 source data that I'll show you is of this BB phantom. It's the shell of a cylinder with a bunch of steel BBs on it. Looking down into the source array, as I mentioned, it's 32 sources arrayed as 2 rows of 16. You see the 4 modules there, and each one has 2 rows that are labeled here as grid A and grid B. As all things like this, when you first try it, it has technical problems. Here's the raw data from one, what we call a super view, looking at the object from all of the sources. This is from 16 of the sources in grid B. That much data is the data collected by the 64 by 192 channels from a single source. And then all of the other ones that you see there are the other 15 sources in that acquisition, looking at data through air in the upper row. And you see the inhomogeneity there is due to problems in the source array. In particular, there's shadowing that's coming about because of imperfect alignment of certain physical parts that are on top of that just before the X-ray window. And unfortunately, they were shadowing the X-ray output of those particular sources. Just below that, you see transmission through the BB phantom. And on the bottom, when you take the ratio and convert it to a projection, you see we're able to recover the data from some of those shadowed regions, but not all. And you see the images of the BBs. The other row also had shadowing problems in different places. We were able to rescue enough of the data to actually image the BB phantom, and you see there one of the stack of slices through 4 of the BBs and the phantom. We will continue to work with this. The source is currently being repaired to correct the problem with the shadowing. I'd like to talk to you very briefly about another idea that we have that we're pursuing, sort of a different way of trying to do inverse geometry CT. The biggest technical challenge with inverse geometry is the source array, and in particular trying to rotate such a complicated structure. And an idea that we're pursuing is might it be possible to do inverse geometry with a stationary source array? And if you had a stationary source then that went around the patient and you were able to turn the sources on and off, you could mimic the rotation of any smaller source array. And in that mode, the only moving parts in the scanner become a collimator and a small detector array that you see there, the detector in red and the collimator in blue. And those parts would rotate, and the appropriate X-ray sources would illuminate at the appropriate times. This is a project that's been pursued by Scott Shea, a student in our group who's in the audience. Ideally, you would like to make a single source ring, and then the detector would rotate within that ring. That's technically quite challenging to do. It may be more feasible to divide that into modules, and so, for example, have 3 source arrays that span roughly a third of the ring around the patient. But in that case, you're likely to have gaps. And so the question that comes up is, can you reconstruct an object even if you have gaps in this stationary source array? And the problem turns out to be that in the rays that connect a gap with another gap, you will never be able to collect that data since you don't have any illumination from either one side or the other. But within that triangle, in the circle, the data are fully sampled, and that becomes your fully sampled field of view. And Scott has done some simulations of that. On the left, you see a conventional cone beam system with 16-centimeter thick volume and cone beam artifacts in the region of the spine, whereas the inverse geometry, stationary source inverse geometry system with 3 arrays is relatively free of those artifacts. You see some other artifacts that we still have to deal with. So to summarize, inverse geometry has some potential advantages: scalable axial coverage with no cone beam artifacts. I didn't show it, but the uniform spatial resolution across the field of view and the virtual bow tie gives us better dose efficiency. The disadvantages is that if you illuminate from many sources, you can't have anti-scatter grids. This is also an advantage because you don't have the X-ray loss in the anti-scatter grid. There are flux challenges and source array complexity. The last of those is perhaps correctable, or we could sidestep it with the stationary source idea. And our next steps in general are to complete the repairs of the 24-source module, do image quality studies, and continue to investigate the stationary source approach. Thank you.
Our final presentation for the morning before we begin our discussion will be given by Andrew Einstein.